To a beautiful mind here. And we are continuing our discussion on chapter 1, differentiation. Okay. And here we're going to be looking at section 1.7, the chain rule. So a couple of objectives here. We like to find the composition of two functions, and we want to differentiate using the chain rule. So first we have a definition. The composed function f composed g, right, notified by this open circle. And g is defined as f composed g is going to be basically the second function inside the first function. The second function inside the first function. So for this example, for f of x equal to x cubed, g of x equals 1 plus x squared, find f compose g and g compose f, okay? With f compose g of x, this means the second function inside the first function. So f of the second function inside the first function. So then this means f of, now g of x is 1 plus x squared. Essentially what we're doing is we're taking the function f of x and replacing each x with the green thing. So if we look at f of x, which is x cubed, so then we're going to say x cubed. We start by replacing each x with a blank set of parentheses. Same thing into each set of blank parentheses. So 1 plus x squared, right? We could expand that out. Let me see if that's what they want us to do. Okay, so they did expand it. So we can go ahead and expand it. Let's go ahead and expand it. I have 1 plus x squared. Now, if you FOIL two of those, right? First and first is 1. It's going to be what? Plus 2x squared x to the 4. I think that's the expansion of that. Then, we need to distribute this binomial over the trinomial. So then first you have a copy of everything because of the 1. So I'm going to say 1 plus 2x squared plus x to the 4. And now if we distribute the x squared, it's going to be plus x squared 2 4. Terms, I think 1 is by itself. We're going to get 3x squared 3x to the 4. Lectures after eating lunch. I totally just want to go to sleep. That's all good. All right. Now that was f compose g. Now let's find g compose f. G compose f, if we reverse the order, second function inside the first, so that's going to be g of f of x. I usually do f of x in this company. G of, now f of x is x cubed. We're just taking the function g and replacing each x with the fuchsia thing. All right, that's why I changed the color, because I think fuchsia begins with f, and it's it looks like pink or whatever. One plus x squared, but then each x in this case is this. As the previous, we get a result. Power we multiply, so 3 times 2 is 6. So there's going to be 1 plus x to the 6. So the whole point of this was to make it clear that the order is important when we're doing composition of functions. The order is not closed under, is not commutative, right? So if we change the order, it can change our answer. Square plus 3x to the 4 plus x to the 6, and then 1 plus x to the 6. Being square root of x and g of x being x minus 1, find f compose g and g compose f. Okay. So compose g of x. That's going to be f of g of x of our g of x is x minus 1. Square root of x. So replace each x with the green thing. Any further? And g compose f of x. This is going to be g of our f of x is this guy. G of now our f of x is square root of x. G of x, which is x minus 1. Rest between my other recording, well, 2 recordings ago. I don't know. Today's just not my day for having energy. It's just one of those days. Okay, we got the square root of x minus 1, and then we have the square root of x minus 1, right? Here. As an exercise for you, and again, just let me know if you need me to work through any of these, and we can work on those separately. The derivative of a composition is given by, so now, if we take the derivative of a composition, it's the derivative of the composition. It's the derivative of the outside function times the derivative of the inside function, right? So you take the derivative with respect to f, or you take the derivative of f first, and then times the derivative of the inside function. So long story short, the chain rule is the derivative of the outside function times the derivative of the inside function. Let's try a few examples. So for y equals this and u equals this, all right. So now, let me think about this. So let's start with dy by du, the derivative of y with respect to u, okay? The derivative of a constant is 0, so that one's going to be gone. This is like 1/2 u to the power of 1/2, right? So then when we take the derivative, that 1/2 comes down. So then there we're going to get 1/2 u to the power of a negative 1/2. Du dx, so the derivative of u with respect to x, this x cubed, the derivative of x cubed is going to be 3x squared. Of a constant is 0. To find when we go to find dy by dx, that's going to come from basically like dy by du times du. x, right? When we do this, these two are going to cancel. So dy by du was the 1/2 u to the minus 1/2. Make that substitution momentarily. Times a 3x squared. And we just need to substitute in u. Have x cubed plus 1 to the minus 1/2 times 3x squared. As here, let's just take it a little step further. Now, looks like we're going to have the square root of x cubed plus 1 okay. 2 times the square root of x cubed plus 1. 3x squared, 2 times the square root of x cubed plus 1. Okay. I'll leave that for you. So in this example, for y equals this and u equals this, find dy by dt. Okay, it's the same thing. Okay. So first, let's find dy by du. So the derivative of y with respect to u is going to be 2u minus 3. And then let's go ahead and find du by dt. That's going to be 5. So then if we want the derivative of y with respect to t, that's going to come from the derivative of y with respect to u times the derivative of u with respect to t. So essentially, these units are going to cancel, and that'll put it in the form that we need. All right. So then that's going to be, and let's go ahead and substitute in our u being 5t minus 1. Minus 3, 5. Let's see how did they expand theirs? Okay, let's go a little further. That 5, 2 here, and what I'm doing is basically 5 times this thing and then 5 times this thing. 2 is 10, so I'm distributing a 10 into those parentheses. So that's going to be 50t minus 10. And then 5 times 3, that's going to be a negative 15 minus 25. Power rule. So right, so I think we kind of have been using the power rule for several examples where basically the exponent, the power comes down and we subtract 1 from the exponent. So that's where the base of the exponent was like a variable. Now what if that base of the power function were a function, right? So that's where the chain rule comes into play. So you have to put the power rule and combine it with the chain rule. So you still bring down the exponent and subtract 1, but now you got to say times the derivative of the inside function, right? So then suppose that g is a differentiable function of x. Then for any real number k, the derivative of the power of a function is going to be the power comes down and we subtract 1. times the derivative of the inside function. So long story short, the derivative of the outside function times the derivative of the inside function. Get this, okay? And f prime of x. So if we focus on the outside function, that 1/2 comes down. I'm just rewriting the inside function for right now. 1 minus 1 is a negative 1/2. Outside function, now we're going to say times the derivative of the inside function. So the inside function, the derivative of 1 is essentially 0, so that's a constant, it's gone. The derivative of x cubed is going to be 3x squared. That negative exponent to the bottom and turn it into and write it as a radical. Let's go ahead and do that really quickly. So we're going to have 2 times the square root 1 plus x cubed. And the extended chain rule, okay? Of x, if we do the first, that's going to be the first, which is this guy, 3x minus 5 to the power of 4. The first times the derivative of the second, so I'm going to say times d by dx, or the derivative of 7 minus x to the power of 10, right? So the first times the derivative of the second plus the second first, d by dx of and let's evaluate those derivatives. So the extended chain rule, the 10 comes down. So I'm going to just write that first. So here, let's get the order. 3x minus 5 to the 4. Seven minus x. Now the derivative of the inside function, that's gone. Derivative of negative x is negative 1. So I'm just going to say times negative 1. To the power of 10. The derivative there is going to be times, we got a 4, 3x minus 5 to the power of 3 times 3. Like terms that we can factor out. Let me see if I can highlight them. We got this 3x minus 5, 3x minus 5. They both have that one. It looks like they also both have the 7 minus x that we can factor. So let's just focus on those. If we factor out the 3x minus 5, they both have at least 3 of those guys. They both have this 7 minus x, and they both have 9 of those guys, right? We pulled those 2 out of each. Let's see what's remaining. You have this negative 10. 3x minus 5 is remaining here. And I think the 7 minus x's are done there, okay? Minus x is there. Three x minus 5s are gone, and we still have times of 12. Okay. Take your time, go slow, and write it all the way out. Like give yourself plenty of space. Okay, so then what I'm going to do is expand and combine like terms on that second part. These first two, I'm just going to bring them down. 3x minus 5 cubed. X. Why do I keep this in the minus? It's so weird. 7 minus x to the power of 9. Okay, so then we're going to get negative 30x plus 50 14 is 84. Might be it. 3x minus 5 cubed minus x to the power of 9 minus 12 is negative 42. 13, so 134. Factor out of 2. There are some common factors there. 21. Up here, right? I think this is a reasonable place to stop. I suggest that we combine the product rule and extended power rule. Let's see. Cube 7 minus x to the 9. They did figure it out was the 2. So then that's a 42. For minus 42x. Factored out the 2, right? Because those had common factor 2. So I'm going to stand by this. This is good. That was an adventure, right? These, you know, you just got to take your time and do your best. Again, I've been leaving the quick checks as exercises for you. And you just have to kind of get my attention if you want me to go through any of those. So then the section summary, the composition of f of x with g of x with f composed g, and is defined as f composed g of x is basically the second function inside the first function. Composed g is not equal to g composed f. The change to differentiate a composition of functions. So when you have the second function inside the first, then the derivative is going to be the derivative of the outside function times the derivative function. Well, if you have the power of a function, then again, the power comes down times the derivative of the inside function. Okay. You know, hopefully that wasn't too terribly bad for you. In general, I know that with me, I can't really follow other people's math, like generally speaking, like when it gets to that meticulous, tedious, you know, a whole bunch of numbers and symbols, you have to like give yourself plenty of space, take your time, go slow. And the way I really get these, I do them myself. Like I'll watch other people doing it and to get a sense of it, but it's not until I do it myself that I really get the nuance of it. You have to do it yourself. I mean, but still get help and work with people, but you don't really get it truly until you start doing it yourself, right? I'm going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Okay, take care. Take care, guys. Peace.